Hello dear students, welcome you all for power system operation and control class. In the previous class we have seen the speed governors where we general the governor operation and steam turbine governing system we have seen. Today we will discuss about the conventional governor. You can see the figure 6.3 where a conventional governor is shown. So the major components are first one is the fly ball speed governor. This is a mechanical device which is speed sensitive and directly adjusts the valve opening via the linkage mechanism. It senses the change in the speed or power output and appropriately initiates the valve opening or closing. You can see there two close, two open is shown in the figure. No, so that is called as a fly ball assembly or fly ball speed governor, which is a mechanical device and obviously it is a speed sensitive and directly adjust the value of the opening or closing of the governor valves. Okay, next is the linkage mechanism. This transforms the flyball movement to the turbine valve through a hydraulic amplifier and provides a feedback from the turbine valve movement. You can see there is a hydraulic amplifier is there. Before that there is a linkage mechanism, means this is a link between the hydraulic amplifier and the flyball assembly, where the feedback from the turbine is also given to the hydraulic amplifier or the flyball movement to the turbine valve through this hydraulic amplifier. So this is the linkage mechanism. Linkage mechanism, obviously the name itself, it is a link between the two. Next is the hydraulic amplifier. It's a hydraulic servo motor interposed between the governor and the valve to build a mechanical force strong enough to operate the steam valves or water gates. So this is the amplifier which is used for the build the mechanical forces strong enough to operate the steam valves or the water gates. Next is the speed changer. It is used to provide the steady state power using output setting of the turbine. So speed changer is changes according to the changes what is taken place with the mechanism. So the figure shows the total a mechanical conventional governor how it is operates. You can see the lower riser speed changer is works, how speed governor works there is it. So different components are shown in this figure. Coming to the next is electronic hydraulic governing system. Where electronic hydraulic governing system is concerned, you can see the figure 6.4 here. There is a speed and power, that is sensing element. There is a E to H converter, then hydraulic amplification speed changer. There is a steam control valve, then turbine. You can see the figure clearly. So what exactly this one? The electronic sensing element senses the speed and power. Obviously we are having different things to measure speed and power, we know. There is some of the speed measuring tachometers are with laser operated. Many things are there. It can sense the speed and also the power. It can be used instead of the flyball governor, which is a mechanical speed sensor used to conventional governor, where the flyball assembly is used in the conventional one. Here we are directly sensing is used. The processing element processes the speed error to obtain the valve opening command. So the processing elements are which are there, that is process the speed error. Actually the main thing is what we need to compare with the reference speed and get the speed error. That error, whether positive or negative error, will make us to operate whether valve open or close, all those things. Okay. So this is done using either PI or PID controllers. The primary amplification is done to obtain the sufficient power to operate the control valves. With the pure governor controller, only the speed error is used to control the valve opening with AGC. Load control is also incorporated. That figure 6.5, you can see there. There is a with pure governor control, the speed error is used to control the valve opening. You can see there. So here with AGC, that is automatic generation control, load control is also incorporated. So here speed reference is also given, load power reference is also given, and whatever generated, whatever actual speed is comparison is done, then it is given to respective controllers, and then control logic is given. The control logic will decide the opening of the valve or closing of the valve. So with the speed controller operating alone, the valve opening is decided by the speed error and the derivative of the speed error. With the load controller acting alone, the valve opening is determined by the output power error. A combination of both used in ALFC, that is automatic load frequency control. The function of the hydraulic amplifier and the speed changer is same as the previously what we are seen in the hydraulic governing system, no, electronic hydraulic governing, same as that one. So this is regarding the electronic hydraulic system. Now we will move to the modes of governor operation. So what is the different modes of governor operation? It is defining the modes of the governor operation. The normal speed is considered as 100% speed and the full load is considered as 100% load. So the first mode of governor operation is the isochronous operation. Isochronous mode operation means the governor maintains a constant speed from no load to full load. See, as the figure shows here, it is called as isochronous governor curve. Here a graph is between the speed, that is speed is in terms of frequency, that is frequency is depending upon speed, and on the x-axis load is there. Even though whatever may be the load, here our speed is set. See, from the no load to full load, speed is 100%, whatever we are having initially. A prime mover and generator operating in the isochronous mode can be maintain the desired output frequency regardless of the load changes as long as the prime mover capacity is not exceeded. This mode is normally used to isolated system or when the generator is required to respond the changes. Okay. The next method is droop mode operation. So you can see here droop mode operation. The speed droop is a decrease in speed or frequency proportional to the load as shown in the figure. See, in this figure 6.7a you can see how output changes. The speed is changing from the no load to full load. You can see there is a delta p which is changes, or the frequency change is nothing but the speed change, or the regulation R is given by the delta f by delta p, or delta f is nothing but f minus f naught. You can see what is f and f naught. Okay, f is at the final frequency, f naught is the initial frequency, or it may be at the w naught, the frequency is f naught, at w you can think it as a frequency f, like that we can have. Then another one is speed droop curve with the change in governor set point, the second one. So you can see in the figure B, the steady state regulation R is given by delta omega by delta p. As I told you, it is a slope of the speed droop characteristics. If the governor with a speed droop is connected to an isolated load, the speed would drop from no load to full load. R can also calculated by delta f by delta p, where delta f is the change in frequency, which is same as delta omega, that is speed. The set point of the governor can be changed so that the nominal speed can be obtained at different outputs. So in this figure it can show us that at different outputs what is the nominal speed we can get. So according to the IEGC, the droop of the governors should be between 3 to 6%. Now, assuming a prime mover generator is in speed droop mode is connected in parallel to another isochronous mode operation, the isochronous unit is known as the swing machine. Now the droop machine will run at the frequency of the isochronous unit. The power output of the droop machine is determined by its speed set point, speed droop and the grid frequency. Now the load is increased, the power of the swing machine will increase to meet the increased load, while the power of the droop machine would remain unchanged. The system can be loaded until the load is equal to the combined maximum output of the swing machine and the set power output of the droop machine. If the system load exceeds, then the frequency will drop. In this setup, if we wish to change a portion of the load met by the droop machine, we need to change in its speed setting. Instead, if the load were to be decreased continuously, the isochronous machine's output will decreases eventually to 0 when the load is equal to set point load of the droop machine. If the load is further decreased, then the frequency will increase and the swing machine will be motorized and trip on the reserve power. So suppose a generator whose governor is acting in isochronous mode is connected to to the utility, its set point will not exactly same as the grid frequency. Therefore, the prime mover may be driven either to full power or into reverse power. So you can go through these different modes of operations. Anyhow, I think asynchronous operation mode is very simple, and droop mode operation you need to read it once again. If you not understood this one, once again you go through this one. Anyhow, I will be sending the notes of this one. So the remaining things we can see in the next class. Thank you.